Welcome everyone. We are going to start a new chapter on second order systems. And by second order system, I mean a system described by a second order differential equation or a set of two first order differential equations. The reason why we start normally by second order system is that will enable us to visualize easily the behavior of the system, and hence we can introduce some of the basic concepts that we see in general in nonlinear systems. However, before we do that, let us first have an overview of what we are going to do. So let us consider a system described by the usual differential equation of x and u, where x belongs to a space of dimension n, and so is f. It is a vector field that belongs to a space of dimension n, and we assume that u is a state feedback control function. So in that case, we would have x dot as a function of f of x. We call that autonomous system. And the autonomous system is actually a time invariant system. So we are going to focus on this class of systems in our coming study. And of course, the system could be of dimension higher than the second order, but as I said, in this chapter we will just consider second order systems. If the system is a second order nonlinear system, we will show later that that nonlinear model can be linearized around the origin, and the resulting linearized model will be in the form x dot equals a times x. So this is the linearized model at the origin. It would be x dot equals ax. We know that this is a popular way to study nonlinear systems, is that we can linearize around the equilibrium point and then study the behavior of the linearized model at or around the equilibrium point. However, the bottom line here is that we get a linear model in the form x dot equals ax, and that linear model should be studied. So that's why in this video I'm going to start by studying the behavior of a linear system, a second order linear system in the form x dot equals ax. And consequently, in the coming video, we'll see how to get from the nonlinear model x dot equals f of x, how to get a linearized model in the form x dot equals a times x. And consequently, you can generalize what we are saying about linear system to the linearized models of a nonlinear system, and of course we will see the limitations of that procedure. So if we consider the second order linear system in the form x dot equals ax, we could find a transformation, linear transformation, in the form z equals transformation matrix T times x, so that we put the linear system in the real Jordan form. So that would be z dot equals the real Jordan matrix times z. In that case, if we assume that the eigenvalues of the system are distinct, so if they are real, the form of GR would be a diagonal matrix with the diagonal components lambda 1 and lambda 2. Here we'll have zeros. Or in the form of alpha and minus beta. Here we'll have beta and alpha. And this is the case of the complex eigenvalues, where the real part would be alpha, and the imaginary part would be plus or minus beta. So let me take the first case where both the eigenvalues are real and distinct. So if we take lambda 2 less than lambda 1 and less than 0, so they are both negative, we call lambda 2 the fast eigenvalue, while lambda 1 is the slow eigenvalue. We can then write the system equations in the new coordinates as z1 dot equals lambda 1 z1 with some initial condition, say z1 0, and similarly z2 dot would be lambda 2 z2 with the initial condition z0 2. In that case, we can solve easily the equations, and the result would be z1 of t would be equal to the initial condition times exponential lambda 1 t, and z2 of t would be the initial condition times exponential lambda 2t. Since both eigenvalues are negative, then we guarantee that as t goes to infinity, we will find z1 going to 0 and z2 also going to 0. However, as I mentioned, lambda 2 is faster, so that means that z2 will go to 0 faster than z1. So if we like to find a relation, if we like to plot z1 and z2 on the phase plane, which means a two-dimensional space with the horizontal axis z1 and the vertical axis z2, we could rewrite the differential equations differently. We could write dz1 over dz2. That is by direct division of the first equation and the second equation. That would be equal to lambda 1 over lambda 2, and here we'll have z1 over z2, and that would lead to dz1 by z1 equals lambda 1 over lambda 2 dz2 by z2, and we can integrate both sides of the equation to obtain a solution. So we'll get here ln z1 equals lambda 1 over lambda 2 ln z2, and of course there should be some constant for to account for the initial condition, so let's call it ln c. So in that case we can write some equation like z1 as equal to c times z2 to the power lambda 1 over lambda 2. So if we like to plot the solution, we can take here z1 as the horizontal axis and z2 as the vertical axis, and of course we are going to assume some initial condition, and we know that the system will go exponentially to the origin. However, since lambda 2 is faster than lambda 1, so we expect the solution to reach z2 equal to 0 faster than z1. So the plot would be something like this. Of course, if we change the initial condition, we can get another solution, and that could be in all regions around the origin, like this. So every plot here would correspond to a certain initial condition. They all go to 0. Each plot here is called a trajectory, and it corresponds of course to a different initial condition. And the family of trajectories that we have drawn here are called the phase portrait of the system. Now, since all trajectories converge to zero, and zero is the equilibrium point for this linear system, so we call here the origin or the zero the stable node. So here the origin is stable node. Now, if you consider a case where lambda 1 and lambda 2 are both positive and they are not equal, so in that case we will notice that the solution both z1 and z2, since the exponent here will be positive, the solution will go to infinity as the time goes to infinity. So we can again plot the trajectories of the system, and we will notice that in this case the origin would be an unstable node. So in that case, these are the trajectories of the system. It will go to infinity. Like this. So this is the second case that we can consider in dealing with distinct eigenvalues. A third possibility could happen is that when we have one of the eigenvalues negative and the other one to be positive. So if we consider lambda 1 to be greater than 0 and lambda 2 to be less than 0, in that case we get an equilibrium point which is called a saddle point. Let's take the horizontal axis to be z1 and the vertical axis to be z2. Since lambda 1 is positive, then we expect the solution for z1 to go to infinity as the time goes to infinity, while we expect the solution for lambda 2 to go to 0 as time goes to infinity. So if we plot the trajectory or the trajectories of the system, we will find something like this. As we can see here, z2 goes to 0, while z1 goes to infinity, and similarly in this quarter, like this, like this, this. But if we start from the vertical axis here, we'll notice that the trajectory will go along z2 axis to be to the 0, and this is the only stable trajectory that we could have on the vertical axis. We call the origin in this case a saddle point. So this is called saddle point of equilibrium, which is x at 0 in our case here. Now we consider the case where we have complex eigenvalues. In that case, as we mentioned, we can write the second order system in the form of the real Jordan matrix times the state vector z, and here we have the Jordan matrix to be alpha and minus beta, beta and alpha, And actually, if we calculate the eigenvalues of this matrix, we will find that the roots will be at alpha plus or minus j beta. So in that case, we can write the differential equations as z1 dot equals alpha z1 minus beta z2, and z2 dot equals beta z1 minus alpha plus alpha z2. To solve the equations in an easier way, we redefine actually the state variables. So I'm going to take r, which is equal to the square root of z1 squared plus z2 squared, and we'll take theta as inverse tan of z2 over z1, and we'll see that that will yield differential equations that are easier to solve. So let us find r dot. R dot in our case would be 1/2 z1 squared plus z2 squared to the power minus 1 over 2, and that should be multiplied by 2 z1 dot plus 2 z2 dot, and of course we can calculate z1 times z1 dot by direct multiplying first equation here by z1, and second equation we'll use it to calculate z2 times z2 dot. That will give us alpha z1 squared minus beta z1 z2, and second term would give beta z1 z2 plus alpha z2 squared. And as we can see, if we take the summation of that, we can find that r dot would be equal to 1 over r alpha r squared, and that of course is equal to alpha r. So this is the first differential equation that we get. We can also calculate theta dot. Theta dot would be 1 over 1 plus z2 over z1 all squared. That's multiplied by z1 z2 dot minus z2 z1 dot, and this is divided by z1 squared. And again, by direct substitution, we can figure out that theta dot is actually equal to beta. If so, we can integrate both differential equations here. So we'll get an equation for r of t, and that would be r naught, some initial value depending on initial condition, exponential alpha t, and theta would be some constant theta naught depending on initial condition plus beta t. This equation is called the logarithmic spiral. So we can plot in the z1 z2 the equation, the solution. So this is z1 and z2. We'll find the solution like this. It's a spiral. However, whether it converge to the origin or go to infinity as the time goes to infinity, that will depend on the value of alpha. And as we can see, alpha is nothing but the real part of the complex root. So if the real part is negative, that means that the system is stable, and it means that the system will go to from the initial condition to the origin. So this would be the direction in case of a negative alpha. So it will go to the origin like this, and we call that stable focus. So the origin in this case is called a stable focus. While if we have alpha greater than 0, in that case the spiral will go to infinity. So this again Z1 and Z2, and as I said, the direction would be in the increasing direction, so that's called unstable focus. How about this is for the case of a positive alpha? If alpha equal to 0, in that case we will get a set of closed curves in the Z1, Z2 plane. This plot that this is Z1 and Z2. In that case we will have series of, we call that center. So this is the three possible situations that we could have if we have complex roots for the. A special case could happen if we have one of the eigenvalues equal to 0 or both of them. So for example, let's assume that lambda 1 is equal to 0 and lambda 2 is not equal to 0. In that case, we will have the differential equations equal z1 dot equals 0 and z2 dot equals the eigenvalue lambda 2 times z2, of course with some initial condition z1 0 and z2 0. So the first equation, the solution of the first differential equation would give z1 of t equals the constant which corresponds to the initial condition, and the second equation will give the exponential solution as usual. So it will be the initial condition z2 0 times the exponential of lambda 2 t. And in that case, of course, it will depend whether lambda 2 is positive or negative. So the solution either will go to 0 or will go to infinity. So if we like to plot the solution in that case, that is z1 and z2. So we notice here, according to this solution, that z1 would be always a constant depending on the initial condition. So the trajectories will be vertical lines. So something like that. For example, if I assume lambda 2 to be negative, then z2 will go to 0. So we will have solutions like this. So this is the case of lambda 2, of course, negative. So this is the case if one of the eigenvalues is 0. If both eigenvalues are zeros, so take the case of lambda 1 equal to lambda 2 equal to 0. In that case, the Jordan matrix will take the form it will have zeros, of course, at the diagonal, but it will have 1 here at the off diagonal. In that case, we can write the differential equations as z1 dot equals z2 and z2 dot equal to 0 with some initial condition. So the solution of the first differential equation will give z1 of t equals z1 0 plus 0 times t, and the second equation will give us the initial condition as a solution all the time. So again, we can plot the trajectories that correspond to the solutions. This is z1 and z2, and we'll find the solution will be either like this or like this. So these are the trajectories that will compromise the phase portrait for the system in this case. As a final note, we noticed actually that the original system equation was x dot equals ax in general, and we used a transformation to get the form z dot equals j z, where j is the real Jordan form. Now, the benefit we got from this transformation is that we get the axes, the z1 and z axes, to be orthogonal, and along these axes we will have the eigenvectors of the system. So that would be like some kind of normalization for the system. So for example, if I assume this to be z1 and this to be z2, then the eigenvectors will be along z1 and z2, and they are orthogonal. And for example, if we consider the phase portrait for the stable node, which looks like this, if we consider the general form, which is x dot equals ax, in that case the eigenvectors will no longer be along the axes. Like for example, if we take this as x1 and this as x2, this is x1 and x2, then in general the eigenvectors would be, say, v1 and v2. They will not be orthogonal, they will not be along the x1 and x2 axes. However, still the phase portrait will be corresponding to a stable node, but it will be rotated, so it will be along the axis v1 and v2, so it approaches actually the origin asymptotically to the v1 axis. Like this, according to the assumption that lambda 2 is more negative than lambda 1, and in the other side it will be like that. So we still get a stable phase portrait of a stable node, and this situation will be repeated in the different cases. So we get the same basic qualitative behavior around the equilibrium point, but as I said, it will be rotated according to the eigenvectors in the general x1 and x2 coordinates. So this completes my presentation of second order linear dynamic system qualitative behavior around the equilibrium point at the origin. In the next video, we'll start talking about second order dynamical nonlinear systems. Thanks.